This is the IHES Summer School, and I'm pleased to introduce our next speaker, Kirsten Wickelgren.
Thank you. It's been a very interesting summer school for me so far. So thank you very much, everyone, for putting this together and the opportunity to speak. This is all joint work with Tom Bachmann that you heard from a few days ago. And we'll start with the application to counting linear subspaces. Let's give ourselves notation for K, a field, and F1 through Fj, homogeneous polynomials that are going to cut out what's called a complete intersection on projective space. So there's the homogeneous coordinates, coordinates of projective space, and we can look at this variety, which is the common zero locus of F1 through Fj. And if this is dimension n minus j, that's what it means for X to be a complete intersection. So we're going to be counting linear subspaces. Let's say explicitly what a linear subspace is. So on our plane in X is a copy of p to the r cut out inside p to the n by linear equations. We're going to let these linear equations have coefficients in some field extension. Okay, inside E. And then we get, it will be on our plane in X if it sits inside X, viewed as a scheme over E. So there's our linear subspaces of dimension R. So the space of all linear subspaces is a Grassmannian. So this is Grassmannian parameterizing PRs in Pn. Equivalently, it's the space of R+1 dimensional subspaces of an n+1 dimensional vector space. And we've got some different choices for notation for this, but let's go with GR, R, N. And here, if we have a subspace W, we can take its projectivization and we get a PR. We can even make it a different color. We have the subspace W, sort of a point in this Grassmannian, goes to its projectivization. And there we've got some notation for Grassmannian. So the Grassmannian.
Kirsten, excuse me, there's a question for you in the chat.
Like you want this. Great, thank you. So Haynes says it's just a closed subscheme. It's not. Oh, and this one too. I guess in principle we could have X be a linear subspace, and then maybe it would be equal. So XE is some interesting variety cut out by equations of different degrees, and inside them they might have points, lines, two-dimensional planes, three-dimensional planes, and I'm just saying that, you know, that explicitly here. That we're allowed to have our linear equations have coefficients in E in some extension. Does that make great? Thank you. So we've got a tautological bundle. And it's the vector bundle, so that over the point corresponding to the subspace W, your fiber is W itself. And we're allowed to do vector space operations on bundles. And the one that comes up for looking at these complete intersections, let's look at sim D of the dual of S. This is the vector bundle on the Grassmannian, which at a point W, we have the degree D polynomials on the vector space W. So let's give ourselves notation for the degrees of the Fi. So let di equal degree Fi, and Fi determines a section of sim di s dual W. Let's call this section sigma I, by sigma I at the point W is Fi restricted to W. Fi is a Fi is a polynomial on the entire vector space. So it restricts to a polynomial on each of the W, and this gives an element of sim di of SW. So from the choice of our equations, we get a section sigma as the sum sigma 1 plus sigma d sigma j section of, let's call this vector bundle V for convenience, of the direct sum of the sim di S dual. Now we can express the space of all R planes in X as the zeros of this section. So let's let FRX, this is the space of R planes in X. It's the subscheme of the Grassmannian determined by sigma equals 0. And it's a result of Debar-Manivelle that for generic Fi, this is smooth of the expected dimension for generic Fi. So why is the vanishing of sigma the space of R planes in X? It's because we have a plane, P of W is in X, if and only if the restriction of Fi to W equals 0 for all these i's. So we know what our dimension is. We've got the space cut out as the zeros of a section of a vector bundle. So the dimension of FR, we'll call this delta, is the dimension of the Grassmannian minus the rank of the vector bundle. And the rank of the vector bundle is the number of polynomials of degree di in our variables, and it's all to be explicit about it is it's di plus r, choose r. So let's do examples when we get a finite count. So we've got, it's finite for lines on a cubic surface, lines on a degree 2n minus 1 hypersurface of dimension n, 3 planes on a degree d hypersurface of dimension 2 plus 1/4 d plus 3, choose 3. To give an example where it's more than a hypersurface, we could take lines on a complete CI for complete intersection of 2 degree n minus 2 polynomials, polys, in Pn. We're going to say n odd because we're going to want all these examples to also be orientable in a second. In any event, there are tons of infinite families of these for not just lines in 3 planes, but all the way up for 2 planes too, for that matter. So in any of these cases, there's some finite number of r-planes. And question is what is that finite number? So when delta equals 0, how many r-planes are in X? And the answer, at least for k equals c, over the complex numbers, when we want to solve equations, we have this nice algebraically closed field. We have a nice topology on it. And this is a classical topological Euler number. We can see that it's the Euler number of the vector bundle we called V. This was the sum of the symmetric powers. And one property of Euler numbers is that they can be computed with respect to any section as a sum over the zeros of the section. And this is valid because the zeros of sigma are isolated. And so we're taking the zeros of the section, GR for Grassmannian, and W is a 0 means this is equal to 0. And it's of some local degree. We can view a section of a vector bundle as a function locally, function from C to the dimension to C to the dimension. C has a nice orientation fixed on it. And then we can take the topological degree of a map of small balls. By the Debar-Manavel result, the zeros of sigma are also simple because the zero locus was smooth. And everything is orientation preserving. So what this gives us is a sum over 1 of these same zeros of sigma. And as we commented above, the zeros of sigma are exactly the r-planes. So this is the number of r-planes in X. In particular, this first equality here shows that the answer doesn't depend on your polynomials. It only depends on their degree. Only depends on the DI as opposed to the FI. So one very pretty example is that there are 27 lines on a cubic surface, a generic cubic surface. generic got off the internet a photo from the Göttingen Universität that's credited to O. Zauzig, and there's a Klepsch cubic surface, and there are 27 lines on it. To go up some dimensions, which means we won't look at it, but there are also, for example, 321,489 three planes on a generic cubic 7-dimensional hypersurface. And for any specific ones you want, you could get this answer. Using cohomology of Grassmannians, the splitting principle, and useful tools. Let's change K from C to R. So when K is equal to R, we want to use an Euler number again. And for this, we need V to be orientable. There's again a way to express this just in terms of the constants we have around. So this is equivalent to this sum of di over r plus 1, di plus r, choose r plus n plus 1 being congruent to 0 mod 2. And all the previous examples are so examples, delta equals 0 orientable, all of those above. And we can again compute the Euler number. It's again can be computed with respect to a section. And again, since the zeros are isolated, we have that this is a sum over the points of the Grassmannian of these zeros. And then there's this local term, local degree of a function. So if we look at sigma in some small neighborhood U of a 0 of W, it's going to look like a function from R to the dimension to the rank, which is the same. And then in coordinates, you'd have, let's say, sigma upper I be the ith coordinate when you view it as a function. And we can take the partials with respect to the coordinates xj on Rn. Let's let this be denoted by the Jacobian of sigma, the determinant of this matrix. Let's make this a little clearer. And then the local degree is the sign, +1 when it's positive, -1 when it's a negative, of this Jacobian. And so what this gives is some +1s and some -1s. This is a weighted count of the R-planes. And it's also a lower bound. While the number of R-planes can vary from, say, a generic 7-dimensional cubic hypersurface to another 7-dimensional generic cubic hypersurface, there is some signed count of these 3 planes, which doesn't. And Finashin and Kharlamov write a paper about the whole family of 3 plane counting problems. And in particular, so they do this on the degree d+1 hypersurface in general. And there is 189 3 planes on a 7-dimensional cubic hypersurface weighted count over R. So with the A1 Euler class introduced in Mark Levine's talks, we can obtain a count over any field.
Sorry, Kirsten, to interrupt. Before you continue, maybe there's a question for you in the Q&A.
That's right. So the Q&A is pointing out that this needs to be an integer, and it is many times. Thanks. Let's talk about A1 Euler classes and numbers. So let's let V over Y be a vector bundle with a section on a smooth scheme Y. A section S. And Barge and Morel defined an Euler class in the oriented Chow of Y twisted by the dual of the determinant. And this Euler class there's a 1 in oriented Chow, and you can push forward the 1 by the section and pull back exactly as Mark outlined last week. Let's list a whole bunch of Euler classes. Although we haven't introduced oriented Chow, it's a sum of cycles with coefficients, and let's not worry about that too much at the moment. And this was further developed by Feazell and Ashok Feazell and Mark Levine. Another description of the Euler class is it's a principal obstruction to having a non-vanishing section. In A1 algebraic topology over a field, Morel develops an Euler class encoding that principal obstruction. In joint work with Jesse Cass, we made an Euler class designed for enumerative problems that was the sum of the degrees over the zeros of S of local degrees of S. This is an Euler number. In a beautiful paper on fundamental classes, de Vlies, Jin, and Kahn give constructions of Euler classes, and in particular, Mark presented using this last week, and one of the things this does is we get Euler classes valued in cohomology theories that are represented by SL-oriented spectra. Another thing that Mark talked to us about was a pairing on the Koszul complex. In joint work between Levine and Raxet, they show that this is the Euler class for the tangent bundle. Mike Hopkins actually, after a talk I gave, eyeballed the pairing on the Koszul and asserted it was the same. And I've heard Mark say a nice story about a similar response of Sayre. I'll just put everybody's name down if that's okay. The last list in our point of view on Euler class list that we have here is to take the opportunity to talk about my women in topology group, looking at the Hochschild homology and putting the pairing that the folks who think of coherent duality in terms of Hochschild homology give us, and showing this is this A1 Euler class, and this is work of Candace Bethea, Nini Arcila Maya, Morgan Opie, Ina Zakarevich. So one of the things done in the paper that this talk is about is to check qualities for some of these. These local degrees and the push forward, and for appropriate E, and the Koszul for general vector bundles. As a warning, there's a very interesting paper of Ashok and Fazell about comparing these two, and they are equal up to a unit, but in a context where there are actually quite a lot of units. It's an interesting class. It's an interesting number, and there are a lot of different points of view on it. For moving forward with the story, let's summarize this by saying when y over k is smooth, the dimension of y is the rank of the bundle, and v is a generalization of orientable called relatively orientable. Then we have an Euler number, I'll call it E of v, living in the Grothendieck-Witt group of K. I'm going to spell out what the Grothendieck-Witt group of K is very explicitly, because it's concrete, and our counts record concrete arithmetic information valued in this group. Let's let A be a ring, and GW of A is going to be the group of formal differences of isomorphism classes of non-degenerate symmetric bilinear forms. And this group of formal differences is called a group completion. And for a field, this has a very nice presentation. So presentation for A equals K, a field, then any bilinear form can be symmetric bilinear form can be diagonalized. So the generators are one-dimensional forms for A and K star over K star squared, as in Mark's talk. A is on the one-dimensional vector space K cross K to K, and we take, as a bilinear form, we take xy to axy, and it just has a few relations. We have that AB equals AB, and A plus B equal, A plus B when that's not 1, plus AB, A plus B. And this implies that there are a bunch of ways to write a special form called the hyperbolic form, that A plus minus A is this hyperbolic form, H 1 plus minus 1. I'll give a whole bunch of explicit examples. The growth indeed fit group of C is that they're up to squares. All elements are the same in C star. So if we just take the underlying dimension of the vector space, the growth indeed fit group of C is Z by the rank. And over R, when we diagonalize, we have some number of ones and minus ones. The difference between those is the signature. And that induces an isomorphism up to a parity condition. For fields like a finite field with Q elements or CT, we have that the first two invariants of quadratic forms coming from the Milnor conjecture invariants give the whole growth indeed fit group. The first two are the rank and the discriminant. That's a determinant of when you write the bilinear form as a matrix. So this goes to Z to K star over K star squared, which, let's say Q is odd, gives Z cross Z mod 2. And then we have invariants coming from the Milnor conjecture, which was a great achievement of A1 homotopy theory. The title of this talk was about integrality results, and that means that we want to use where the vector bundle is defined. If it's defined over Z or some sort of ring of integers, we want to compute or say things about the computation of what the Euler number is. So let's also say that the growth indeed fit group of the integers, although there are many very interesting, highly non-trivial, non-degenerate symmetric bilinear forms over Z, once you group complete, you only get Z cross Z. It's a number of ones and number of minus ones. For example, sitting inside GW of Q, or GW of R, maybe more straightforwardly. We have a Milnor exact sequence giving us the growth indeed fit group of Z1 over N, and it'll sit inside the growth indeed fit group of Q, and then there's some boundary maps to the fit group is the growth indeed fit group divided by the hyperbolic form for Q not dividing N. The last thing we'll need to state results are the explicitly giving transfers. We can assume the only thing we'll need to write down theorems is transfers for an extension of fields KL that we can assume to be finite separable, because the Debar-Manivelle result will say that our zero locus is smooth and so corresponds to separable extensions. And then we will have a transfer map from L over K, from the growth indeed fit group of L to the growth indeed fit group of K. And it'll take a bilinear form, beta V cross V to L, and I'll take its class to the composition of beta with the sum of the Galois conjugates, the trace from Galois theory. let's talk more about the about growth indeed fit. But I want to pause for any questions so far. If you think of others, please don't hesitate to interrupt. So the GW of fields pieces together to make an unramified sheaf by a procedure in Morel's A1 algebraic topology. So it gives unramified sheaf GW, say on smooth schemes over K. And the sections over X, they're inside the sections on K of X, on the field of functions of X. And you can extend over any closed subset of codimension at least 2. It's given by intersection of kernels of certain boundary maps for codimension 1 points. And it has an alternative description. It's the sheafification in the Nisnevich or Zariski topology of sending X to GW of X, where now this means the symmetric non-degenerate bilinear forms on vector bundles on our X. And this is a great sheaf. But from the perspective of descent, sheafifying isomorphism classes is an odd thing to do. When if we want to glue together objects, we not only want to know they're isomorphic on overlaps, we might want to keep track of the data of that isomorphism and have it satisfy conditions. So one thing that comes up is that you can have a sheaf of spaces version. Make it a curly GW. So let bilinear of X be the space of vector bundles with a symmetric, non-degenerate bilinear form. And then we can sheafify the group completion of this. So let's let 1/2 be invertible. Let's let these be schemes over Z1/2, and have this be a sheaf valued in spaces. And we'll let it be the sheafification of X goes to the group completion of these bilinear forms. And there's a map to the sheaf of spaces associated to Hermitian K theory. We've got a homotopy invariant version on the right, and our sheaf version of growth indeed bit sheaves on the left. We can take Euler classes in Hermitian K theory or related theories and get good functoriality properties associated with them to give us integrality results. Let's get back to counting R planes and less questions. Yes. So it's necessary to invert 2 when considering duality. So bilinear forms, there are a lot of different, when 2 is not invertible, bilinear forms and quadratic forms are different. Turns out there are a lot of different variants for notions of a duality on vector bundles when two is not invertible. It makes Hermitian K-theory defined with current machinery. And there are a lot of interesting things to say about inverting two. So thank you for the question. Returning to counting R-planes. On complete intersections. Let's list some things we know. In joint work with Jesse Cass, we computed a count of lines on a cubic surface, which is the computation of the Euler number for sim3 of S dual on the Grassmannian, and it is 15, 1 plus 12 times minus 1. And this is also a sum over the lines of an index involving the field of definition of the line and some information about how the tangent plane spins along the line. This is for K, a field. And Mark Levine developed a theory of bit-valued characteristic classes and computes that the Euler number of sim of 2D minus 1 of S dual counting lines on PD plus 1 is 2D minus 1 factorial factorial. I'll tell you what that means. Plus a multiple of H, and the multiple of H is designed to make, so EC for Euler number of complex points minus 2D minus 1 factorial factorial over 2 times this hyperbolic form. So here 2D minus 1 factorial factorial is 2D minus 1 times 2D minus 3 times 1. And so K is a field with characteristic prime to 2 and times 2D minus 1. And EC is the normal topological Euler number of the complex points of C. Stephen McKean gave a enrichment of Bezout's theorem along with geometric interpretations of local indices, and that gives the calculation of vector bundles, so counting points on Pn, that's just Pn, as a multiple of H. And Sabrina Pauli, also along with interesting geometric interpretations, redoes the cubic surface and does the quintic threefold with a theory of dynamic intersections. You can hear her talk about this at motives and whatnot coming soon. So we have enriched counts of R-planes. Let's formalize this notation EC. So let's let, it's on July 29th. Thank you. So let's let EC be this Euler number of the complex points, and ER be the Euler number of the real points. And a theorem I'd like to talk about from this paper is that the enriched count is the sum of ones and minus ones that you would get from the real and complex point counts. So let's let R be a ring with 1/2 in R. And you can also do just a field of characteristic 2. We'll consider the vector bundle we started with, the sum of the di symmetric power of the dual tautological over the Grassmannian, and let's let it be relatively oriented with dimension of V, the rank of V is the dimension of the Grassmannian. So this has, we can rewrite this in terms of parity conditions and sum conditions. So i.e. we want the sum of di over r plus 1, di plus r, choose r, plus n plus 1, congruent to 0, mod 2, and the dimension equaling the rank, dimension of Grassmannian, r plus 1 times n minus r is the rank, di plus r, choose r. And so then these vector bundles that we were interested in, the Euler number is EC plus ER over 2 times 1 plus EC minus ER over 2 times negative 1. And for example, we can get an enriched count of 3 planes on a generic 7-dimensional cubic hypersurface. So there are 160,839 1 plus 160,650 minus 1, 3 planes in a 7-dimensional cubic hypersurface. And to put this back in terms of counting R planes, if we take the sum over the R planes, we'll call the R plane P in our complete intersection X of this trace, and we know it's for a separable field extension by Debar-Manivelle of the Jacobian. We express our function sigma in terms of local coordinates and take some derivatives, then this is the same number up here. And while the number on the right-hand side is some ones and some minus ones, these are not, in general, sums of ones and minus ones. They just have to sum to them. And as suggested by the title, this is proven with an integrality result. The count of the lines on X reduced to a bundle on a Grassmannian that was defined over Z. It's the section that is defined over the interesting equations of X. And that's why the left-hand side here has all sorts of interesting summands. And the right-hand side picks up the fact that the Grassmannian is defined over Z. Theorem 2, this is all joint with Tom Bachmann. So let's let V over Y be a relatively oriented vector bundle with v and y defined over z adjoin 1 over d factorial, and d is greater than or equal to 2, with y smooth and proper, Sn for smooth and proper over the same base. Then the Euler number has to be in the subring generated by -1 and the 2, 3, all the way up to d inside GW of k. And in the case of d equals 2, this leaves 2 possibilities. So then either E of v is the quantity, I think maybe I'll still be able to paste it, this quantity here, or it's what we get by putting in a single 2, but keeping the signature the same. We can distinguish between these possibilities by taking an Euler number over some single prime where 2 is not a square. And in order to prove the result about the symmetric powers, we use a characteristic class argument to get rid of this second possibility. The characteristic class argument owes a lot to Mark Levine's fit value characteristic classes. This would be a good time to pause for questions. Are there any? All right. Theorem 2 is proven by using an Euler class for good SL-oriented theory, for example, KO. The d greater than or equal to 2 restriction comes from wanting to use KO. And there is currently a collaboration on KO without inverting 2 with Baptiste, Calmez, Emmanuel Dotto, Jonathan Harpaz, Fabian Hebestrait, Marcus Land, Christian Moy, Dennis Nardin, Thomas Nikolaus, Wolfgang Stamm, and Marcus Spitzweg, I understand also has work around this. Let's put that. Let's put Marcus Spitzweg here too. So my understanding is that it is expected that they will show that if you take K theory, let's call that KGL, and taking a vector space to its dual gives a C2 action, and you can take a homotopy fixed points of C2, and it's expected that if you make a substitute for Hermitian K theory by taking the homotopy fixed points of KGL and completing it too, that it can be shown that this is the Grothendieck fit group of Z completed it too. So this exists over at Z. So it exists over Z. It's SL oriented, and there's a, you can read about it in a paper of Bachmann and Mike Hopkins. And while it doesn't respect base change, it does have some maps. And so this is sufficient to show the same integrality statement for d equals 1. To show the integrality result, theorem 2, for d equals 1, because the Euler number with respect, if we let this gadget be ko prime, then the Euler number with respect to ko prime, it's here, and there is enough functoriality so that it will have to map to the, if we pull back to z adjoining 1/2 to ko prime, it'll map to the corresponding number. Moreover, there's a map from ko to ko prime, giving that the Euler number when ko exists over 1/2 maps here too. And the since these two elements map to the same element in there, they determine an element of the fiber product. Of GW of Z 1/2, GW of Z completed at 2, over GW of Z 1/2 completed at 2. And this is GW of Z. So we'd get this stronger integrality result with that work. In the spirit of summer school, I'd like to end with some open problems. The 0th open problem can be expressed somewhat facetiously like this. There are a lot of great results in Eisenbud-Harris's 3264 and all that, or Fulton's intersection theory, that give interesting enumerative results. And there are beautiful enumerative results having deep connections to many areas of mathematics. So the 0th problem is, can A1 homotopy theory enrich them? So take a problem from Eisenbud-Harris 3264 and all that. Fulton intersection theory. Let's give more of a preamble to this question. So there are beautiful results in A1 enumerative, in enumerative geometry. Can A1 homotopy theory enrich them? In enumerative geometry, can A1 homotopy theory enrich them? I don't think, I wrote down 2 taken somewhat haphazardly from Eisenbud-Harris. I don't have time to write them down, but let me just read so that we're on the same page about what question 0 is trying to suggest. So let V1 through V2n be general tangent vector fields in Pn. At how many points of Pn is there a cotangent vector annihilated by all of them? And another one is given 4 curves, C1, C2, C3, C4, and P3. degrees, D1, D2, D3, D4, how many lines meet general translates of all four. I'll add these to the notes and put them in. To be less hand-wavy about this, in the corollary above, we didn't have the analog of of interesting descriptions in terms of the complete intersection itself. So geometric interpretation in terms of X, they're very concrete examples of this for this Jacobian, which is sort of living on the moduli space, so beyond cubic surface, quintic threefold, the zoo. To connect up with Marco Riballo's talk, the Hochschild homology of that matrix factorization algebra that showed up, it has a pairing on it, and that pairing is the A1 Milnor number of the singularity, an element of the growth indeed Witt group. But there's also inside this K-naught of varieties, this cut and paste relation, there's this motivic Milnor fiber and a compactly supported A1 Euler characteristic that Mark Levine told us about. This should be all equal. And the list should continue. You lose certain tools and you gain others. For example, Ananievsky's beautiful splitting principle. The multiplicativity of Euler numbers in exact sequences is no longer nearly as useful because you really can't divide. But the Koszul interpretation of Euler numbers gives you some control in exact sequences, but in general it's hard. So are there better tools? There is really structure here and an arithmetic information that lies away from C. And what is it? I'll stop there.
Okay. Thank you, Kirsten, for a wonderful talk. So let's hear some questions. And maybe I can ask by asking you if there's a connection between your work and oriented Schubert calculus.
So Matthias Wendt, absolutely. Matthias Wendt has information on the oriented Chow of Grassmannians in terms of some generalizations of Schubert calculus, and that gives other interesting ways to compute these Euler numbers. It doesn't directly use it, but there is interesting things to be said about that.
Okay, great.
I have a question. Show my face. So this last question, the A1 Milnor number equals the Euler characteristic of the motivic Milnor fiber. You said the left-hand side comes from a pairing on Hochschild homology. Can you say a little bit more about that?
Yeah. I think maybe a better way to start with what the A1 Milnor number is if you have a point P of f equals 0, the A1 Milnor number, if this P is singularity, can be defined to be this local degree at P of the gradient of f. But then this is also the Hochschild homology of this matrix factorizations for f. And that's by explicitly, Marco told us that this was the Jacobian ring. This local degree can be computed as the Jacobian ring, and this can be computed as the Jacobian ring, and the pairing on Hochschild homology is the same. So we get this equality here. So this one wouldn't be part of the problem, and then this one I think is open.
What pairing is there on Hochschild homology?
Great. So Lippmann and I'm blanking. So there's even a six-functor formalism in Hochschild homology, and it's a way of expressing things about coherent duality in terms of Hochschild homology. And I am embarrassingly blanking on the important names involved in constructing that pairing. But it's also, in this context, we wrote it down in the Women in Topology group
Okay. Great. So, and you're too young to be blanking on these things.
Thanks, I appreciate that.
Okay, and there's a nice question in the Q&A, Kirsten, if you can see that.
Yes, so so for over a finite field, so, the three planes that give you a square. So over a finite field, we had we have this this growth and defit group, and so in particular, we're going to have a parity condition coming from three planes associated to square or non-square local contributions. And if you sum all of those non-square over odd degree field extensions with the square ones over even degree field extensions, you'll have to get an even number of those. And over things like cubic surface, this corresponds to the difference between hyperbolic and elliptic lines. And if you come up with a sort of intrinsic to the complete intersection definition of what it means for this discriminant to be square or non-square, or more generally what that Jacobian means, then you get a concrete, totally independent of any A1 homotopy theory restriction on that complete intersection. But even in terms of the Jacobian, we get this even parity condition. So by motivic, by A1 Milnor number, we meant the left-hand side, and then by motivic Milnor fiber, I meant the construction that gives you this element of K-naught of varieties with this motivic integration. So it's a, yes. The construction, the construction is a little involved. The way I've seen it doesn't directly use Ayub's nearby cycles functors, but I wouldn't be surprised if that's my not knowing how to show the two are closely related.
Okay, great. Then I have another question, because in this homotopy limit problem, you're completing at 2. Is that so? So you
Yes.
You don't expect that we need to complete with respect to the Huffmap eta? So just
as far as I know, but I think Tom would be the better person to answer this question.
Okay, then in the Q&A, there's another question.
Yes, yeah, this is the, thank you. So Cass. Jesse Leo Cass, and I did work on A1 Milnor numbers. Thank you, Stephen.
Okay, great. Any other questions? I don't think so. So thanks again, Kirsten, for a wonderful talk. And see you all again tomorrow. We start 1 p.m. Paris time. Thanks.
Kirsten, could you recall, please, 189, 3 planes and 7 oversea, right?
That's right, yes. So it should be.
Because, because your result of here it is, yeah. Or general field 106,000, blah, blah, blah. This angle bracket 1, angle bracket minus 1 collapsed to 189, I think, in the end.
The difference between these two is 189.
Yeah, I mean, we subtract, yeah, and 189, but.
I still have a stupid question. Do you really need to invert 2 for working with GW? I mean, Morel in his book, he said that you can use Hellman, Karpenko, Merkuriev. So, I mean, if you replace quadratic forms by bilinear forms, so there's a presentation of GW, the theory is worked out completely by Hellman, Karpenko, and Merkuriev. And so I don't know.
I think GW with an underline is great. So the unramified shape. Actually, though, could you tell me again? So Karpenko.
Hellman, E-L-M-A-N, Karpenko, Merkuriev, the algebraic and geometric theory of quadratic forms. Maybe I should have asked that question sooner.
So the main theorem holds also for fields of characteristic 2, even without any.
The presentation of GW, yeah. That's what Morel's using.
Yes, and also, I mean, this, even though I said 1/2 here, this could also be.
Which one? Show me again.
Here, this could be a field of characteristic 2,
yeah.
if we wanted, using Morel's, using bilinear forms, using GW underline. So here, I think everything is totally okay in characteristic 2. However, okay. If you want to do this, I think then there really are problems with
KO, yeah.
And with proving this with something else. I know Tom, who's still here but muted, this effective cover of the sphere. And I mean, there would be multiple possibilities. And again, Tom is the person who has great things to say about these possibilities. But I think without inverting 2.
Yeah, I know. Really, so as soon as you are using Chovit or KO, you are always working over fields of characteristic different from 2. So, but yeah. So hopefully this this huge bunch of offers will complete the picture. Thanks.
Thank you.